All right. Well, but remember, it's the limit. It was supposed to be the limit of the SNs that this thing was equal to. It's supposed to be the square root of 2 pi. And somehow we're coming up with the square root of pi over n.
What is it supposed to be?
It's supposed to be the square root of 2 pi, and we'll come up with the square root of pi over n. So somewhere along the line, I have my logic is effective somewhere. That's a damn sure. That square root of n, this n can't be there. So somewhere in there, there's an algebraic mistake, and the n's not there, and there's a 2 with the square root of pi. The square root of pi part we got. The n can't be there, and there isn't a factor of 2 in front of it. I can't find it. I'm not sure where it is. Homework problem. Where did I go wrong? I'm not sure. I might have to do this with Mabel just to keep myself straight up. But you see approximately how to do this. Okay? All right. I'll get off that now. We'll do some theoretical stuff, and at least I think I can explain. It irritates me that I can't get that. Should be the square root of 2 pi. I keep coming up with the square root of pi over n. N has got to be 1. In this little fancy argument, this is where somewhere in here there's an n that isn't gets divided out or something. I'm not sure how, but you'd have to go over that with a fine-tooth comb. Anyway, back in the day, that's how you got n factorial, an estimate for n factorial. You know, what was an early application? Those of you that take probability and stats. You know, when you do the binomial distribution, you need the binomial coefficients for big N's and big K's, right? So if you're doing that in 1800, and all you have is this formula, you're going to be heavily reliant on Stirling's formula. There's another way of getting that constant square root of 2 pi using complex variables. But this is probably the way that Stirling himself did it. And I was trying to reproduce it, and obviously screwed up. Well, anyway, okay.
I had a question.
Yes, sir.
What, I don't know if we talked about this last week, but you were using the trapezoidal hole. Is that something that can't naturally wipe from Cauchy's integral? Or
No.
that's something he just talks about, just as he uses the trapezoidal hole.
Yeah. It's what it does is it gives you the log points. It gives you the log points, and then of course when you started log of 1 is 0, so that drops out, and then you have exactly twice each log as you go along, which is great because you have half of double each log, and the whole thing collapses to the sum of ln2, ln3, ln4, ln5, up to ln n, which is ln of n factorial. So it hands that right to you. If you use the trapezoid rule, that falls out immediately. Every derivation of Stirling's formula I have seen tries to integrate ln n or ln x with some approximation, and then the hard part at the end is to get the correct constant. Many textbooks, even the elementary or first level graduate, first year graduate textbook, will get all the n to the n over e to the n times the square root of n, and then they'll just tell you, by the way, the constant square root of 2 pi. What we were trying to do there is difficult to do, and is not ordinarily done in province stat books. It's just handed to me. I was hoping that I've got to solve that someday here and post it, just because now it's become a quest. There's something there. We're very, very close. We're within, Stirling was aware of Wallace's result and knew this little trick about getting the limit. He must have done something very much like this. Well, anyway. I'd like to develop fundamental theorem of calculus for the Cauchy integral. What is a fundamental theorem of calculus? I say a fundamental theorem of calculus because when you take calculus, you are led to believe that there's the fundamental theorem of calculus. But of course, for every integral definition, there is a fundamental theorem of calculus. What generically is a fundamental theorem of calculus? It consists of several parts. The first part always is a statement about, given some definition of definite integral, what functions are integral? You know, there's Cauchy integrable functions, Riemann integrable functions, Lebesgue integrable functions that are more than the ones that are Riemann. And Kurzweil functions, more of those are integrable than Lebesgue functions. So it's a statement, first of all, about what functions are integrable using a fixed known definition of integral. The second part is evaluative. Okay, now that you have your final definition, other than appealing to the definition to do every integral, wouldn't that be a pain? Remember we did the integral of the square of a parabola by actually partitioning and summing things up and taking limit. You'd be stuck with that unless you had a handy-dandy way of recovering, as the author says, recovering or reconstructing the function from its derivative. So the second part of a fundamental theorem of calculus, once you have a given integral definition, is to come up with an evaluation scheme that involves a primitive. So you typically are establishing the result that the integral from a to b of f of x dx is a primitive of f of x, capital F of x, usually evaluated at the upper limit minus the same thing at the lower limit. That's the second part, the evaluation part. Everybody, no matter what the definition is, the easy integrals are always evaluated that way. We saw last week that the Henstock-Kurzweil integral, as well as the Lebesgue integral, would integrate the Dirichlet salt and pepper function. Remember what that is? The function that's one on the rationals and 0 on the irrationals. So the Riemann integral and the Cauchy integral can't handle it. So there's no point in even discussing an evaluation method. The Lebesgue integral and the Henstock-Kurzweil integral will give you a sum that converges. So the integral exists, but what's the derivative of that sort of, the evaluation? It doesn't, there's no primitive that you can use to evaluate, right? That's okay. That's okay. You still have the integral existing. It's just that you can't use the evaluative framework that we're used to when you learn when you first encounter calculus. So there's no primitive of the Dirichlet function that you can evaluate here and there and take the difference. But you can do the Lebesgue or Henstock-Kurzweil integral of that function. So fine. For the Cauchy integral, we'd like to decide what functions are guaranteed to have a Cauchy integral, integrable in the Cauchy sense, and then as a secondary object within our fundamental theory of calculus, Cauchy style, is what's an evaluative method. If we can find a primitive and take the difference of the primitive, evaluate it with upper and lower limits, maybe that'll be it. We have to show that, but that's our goal. So fundamental theorem of calculus has two parts: definition of the integral and evaluation procedure. So in some calc books, they break that into two pieces, and it sort of gets confusing. It's like, here's the definition, and here's what it exists. That's fundamental theorem of calculus, the first fundamental theorem of calculus. Then later on, a few pages later, the second fundamental theorem of calculus. Oh, by the way, you integrate that this way, finding the primitive. The book discusses two approaches: recovering a function from its derivative and recovering it from a primitive. So you can have it on either side there and get the other. If you have the primitive to get the other function, you differentiate, and if you have the function that you can integrate to find the primitive, you have to integrate it, right? So you would integrate from A to X, little f of x dx, and that would give you capital F at x. So from the little function, you'll find the primitive. You can go either way on that. So we'd like to get conditions for reconstructing one from the other. It's nice when you have those. The